Tonight, we have an absolutely wonderful lecture for you. We're really excited that Dr. Don Lincoln has agreed to speak. Dr. Don Lincoln is a senior scientist at Fermilab, America's leading particle physics laboratory, and was a member of the teams that discovered the top quark in 1995 and the Higgs boson in 2012. Lincoln is also an avid popularizer of science. He has written several books for the public, most recently, The Large Hadron Collider. He also writes for many online venues like CNN, Big Think, Scientific American, and many others. He appears frequently, as you may know, on the Fermilab YouTube channel, and he has made several video courses available through the Great Courses Company. He is the recipient of the 2013 Outreach Prize from the European Physical Society and the 2017 Gemant Award from the American Institute of Physics. He's a fellow of the American Physical Society and the American Association for the Advancement of Science. And we are so lucky to have him here today. This is going to be an absolutely wonderful lecture. And with that, I will pass it over to Don.
Well, thank you, Becky. I'll try to live up to that ringing introduction. And welcome to everybody who's come to hear tonight's lecture. So I was asked to give a lecture, and I thought, what could I do? I decided I was going to go big. So I want to talk about the birth, life, and death of the universe. Now, with only an hour, I obviously can't get into too much details, so I'm going to tell this from 40,000 feet. And because every time I use an imperial measure, someone gets mad and says that this is a scientific institution, I should use metric. So I say it's 12,000 meters for the people who care about that sort of thing. All right, so, but before we get into this sort of grand tale of the universe, we need to remind ourselves of some things. And because when we talk about the universe as a whole, we need to remember that it's made of various components. And in the lifespan of the universe, these components are created. And so as I go through talking about how these particles, these objects came into existence as the universe expanded and cooled, I thought it's probably worthwhile to remind you of them. So the smallest living thing is a virus, and you may say that viruses are not alive, and you're probably right about that, but it's close. And they're very small. They're 10 to the minus 7th meters. So you know how big a millimeter is? And you could put 10,000 viruses in a millimeter. So that's very small. But then we know, of course, that matter is made up of molecules, and molecules are much smaller. Molecules are made of atoms. Atoms, of course, have a nucleus at the center with electrons swirling around the outside. At the center of the atoms, we have protons and neutrons. So these are particles that I will talk a little bit about as I talk about how the universe began, how the protons and neutrons were formed from nothing, or at least from energy. Inside the protons and neutrons are particles called quarks, which are the smallest particles we know of, and they're very tiny. We don't know how big they are, but we know that they are much small. You know, if you compare the size of a virus to us, a quark is much smaller than the virus compared with the same scale. So these are the building blocks that will be created as I talk about how the universe came into existence. In addition, we have forces of nature. And this is kind of important because at early times, we think it's maybe possible that these different forces didn't appear to be different. For instance, we know that electricity and magnetism act very differently, but in the 1800s, it was understood that they were really the same thing, a thing called electromagnetism. Now, the four forces that we know of now are gravity, which is the most familiar. We have electromagnetism, which is, of course, the mix of electricity and magnetism. It also explains light. But then we also have two forces that are only relevant at the nucleus. And so these forces are things that sort of also need to be taken into account to find out when they get blended together and when they become separated. So that's just a real simple reminder And I really like this graphic here, which I can't take credit for, but it sort of wraps up everything we know about the universe or about the subatomic universe. We have the quarks, and quarks are found inside protons and neutrons. So that's sort of the nucleus part of matter. The leptons, the most familiar is the electron. And of course, with electrons and protons and neutrons, you make up atoms. So those things in a yellow box are basically what makes up us. The other particles are things that have been discovered, some of them here at Fermilab and some at other places. On the right-hand side, we have forces. The forces have particles. I'm not going to talk anything at all about this, but I wanted to remind you that these building blocks had to have come into existence somehow in the evolution of the universe to reveal where we are now. But we're not talking about the subatomic world. What we're talking about is the universe. So this, of course, is not a picture of the entire universe. We don't know quite how to do that. It's a really rather lovely photograph of a quintet of galaxies called Stephan's quintet. So you see these 5 galaxies all near one another. And that's what we're really going to talk about. We would like to talk about how this came into existence. Which brings me back to what I promised I would do in the beginning. Talk about the birth, the life, and the death of the universe. And to do that, we have to remember that there are phases in this story. When we talk about the universe has a beginning, but it also has an end. That story has a middle. So that's where we are now, where we live. We live in the middle of the lifespan of the universe. But if we want to understand the entire universe, we also need to know what came before. So this little guy here, that's his mom and her mom and her mom. There's something that, every thing had a cause before it. And we want to try to understand the causes and perhaps even the cause of the universe, which is extremely difficult, as we will see. And then, of course, we need to know what comes after. And that we have actually a little bit more of a handle on because we sort of kind of understand what's going on now. We understand the rules of the universe. And from that, we can actually project forward in time. It's easier to look forward than it is to look back before the beginning. So this is a nice metaphor of humans. However, this is really kind of the way people might think about it. So we have what we call the Big Bang, and I wrote cringe under it because the word Big Bang is problematic, perhaps, in the sense that people use it for different things. Some people talk about it as the process of expansion. Some people talk about it as the absolute moment in which the universe came into existence. And because people use the terms interchangeably, sometimes communication is difficult. But anyways, this sort of shows what we want to talk about. We want to talk about what came before our universe came into existence. We want to talk about how the universe evolved into the one we see in the night sky when we look outside and see the stars and the galaxies. And then we want to project forward to what will happen in the very, very far future. Now, when we do this, we have to realize that there are some limitations to what we know. And I like this slide because it reminds us of something sort of fundamental about knowledge. When we look at this scene, we see a lamp, and underneath the lamp, there's a lot of light. So that guy, if he goes under the lamp, knows an awful lot near where that is. But as he looks off into the distance, we see this fence drifting away. The edges of the fence, we can't see what they are. And this reminds us that when we do this sort of science, when we talk about the life, the birth, and the death of the universe, that there are things that we know better than others. And so here I have perhaps trying to steal from that metaphor of the street lamp. So there is a place, the universe was created, came into existence 14 billion years ago. So we have here on the right-hand side, 14 billion years, that's now, and that's the brightest area. That's the location where we know the most and we know the best. As we go backward in time at 9 billion years, 100 billion years, you see that it starts to get dimmer because our knowledge is not as strong there. And prior to time zero, you see it's black. We really don't know anything about what happened prior to the beginning of our universe. And of course, as we look forward into the future, we have the same problem. The problem is that our knowledge and our understanding and our predictions become less and less reliable. So here we have sort of mileposts, and I'm going to talk about each of these. You don't have to worry about reading them all right now. We are going to talk about the prehistory. We're going to talk about, see here, I've called it the Big Bang, and you'll see why that's maybe a troubling phrase. And then nucleosynthesis is the creation of the nucleus of atoms, protons and neutrons. We have this thing called the CMB, which is the photograph. We are able to photograph the remnants of the fireball of the Big Bang. And I'll actually show a picture of that. So that's something that we know. So we have some physical understanding because we've taken data at that time about 380,000 years after the Big Bang. Then a little later, galaxies came into existence. There's this thing that called dark energy, which will not only qualitatively, but quantitatively change the future evolution of what the universe, what we predict will happen in the far future of the universe. And so then we have now. But remember this metaphor of bright lights and fading off into dimness, because I will tell you some things that we're certain about, but you're going to hear a lot of speculation in this talk. You're going to hear best guesses, and you're going to hear about places where we just really don't know the answer. And that's, part of this grand story that people have been trying to figure out for thousands of years. So what I want to do is I would like to start and talk about what we know. I'm not going to talk about the prehistory in the beginning, nor am I going to talk about the end. I'm going to talk about what we know about the evolution of the universe from the moment it came into existence until now. And so we will start by breaking up the history, the lifestyle or lifespan of the universe into different eras. And these eras have different levels of understanding associated with them. So let's start by talking about the Big Bang, or again, the beginning of the universe. So this is from very early times. And what is the Big Bang? So this is where we start getting into the definition and sometimes the difficulty people have for using different language. What the Big Bang really is it simply is that the universe is expanding. And if the universe is expanding, it was smaller and hotter and it was denser at earlier times. The Big Bang is still ongoing. The Big Bang is sort of an explosion of space. And like any explosion, you have the moment, the flash. If you shoot off a firecracker, there's a flash, but there's also the time of the expanding gases after the explosion. And that's all part of that one process. The Big Bang is actually continuing today because the universe continues to expand. What the Big Bang isn't, and I will demonstrate this more, I'll give you better examples. The Big Bang isn't an explosion. And when I say it's not the actual moment when the expansion began, that's because it's really the ongoing expansion, which continues today. However, people do often call the moment where the universe began as the Big Bang. So this shows you my preferences myself. What the Big Bang is not is something that occurred at a place, and I'll show you this misconception a little later. And here's another thing that you may have heard, that the entire universe was compressed into a singularity. That is kind of true, but not completely true. And this causes trouble because people who take that literally then can go into kind of a wrong direction when they try to understand how the universe began. And then finally, it's complicated. We'll return to time equals zero because that is a really complicated place where our knowledge is quite poor. So let's start by breaking up into this first saga. The time equals zero. This is the time where our universe began, to what we call the Planck time, which is 5 × 10 to the minus 44 seconds. So this is a tiny split fraction of the universe. And so what do we know about that? Well, one thing we know is that general relativity doesn't apply. General relativity was Einstein's theory that described the behavior of space and time and matter and energy. And what we know is, and this is something that we actually truly do know, that before the Planck time, Einstein's theory breaks. We know it breaks. There must be something else going on at that early time, and we don't know what it is. And because of that, we are really quite ignorant of this early point in the universe. So there's some speculation, and certainly I don't mean to suggest that people haven't thought about this, but this is speculation. It's not guaranteed to be true. It could be wrong. But what we think is maybe that gravity, what I call the quantum forces, the forces that govern the subatomic world, perhaps they're indistinguishable. Perhaps there's one force, and those two things, gravity and the quantum forces, are just different features, different facets of that one fundamental force. If you believe general relativity, the concepts of space and time are meaningless, because prior to this time, prior to this Planck time, Einstein's theory says that space doesn't exist. Space comes into existence and time comes into existence. Now, this is speculation because we know the theory actually doesn't apply at these early times. So when you hear people say that space began and time began at the moment where the universe began, that is a statement from a theory that we know to be wrong. Now, it's not ridiculous, and it's very sensible, and that theory is a fantastic theory. But all theories have limitations, and we have pushed it when we talk about this realm, this era. We've pushed it into a place where we know it doesn't work. This is the realm of what we call quantum gravity. This is the realm where we need to develop a new theory of gravity, which nobody knows how to do, a theory of gravity that works on the ultra microscopic scales. And we don't know much. And so we have to be honest. In this period, we really are quite blind. And that's why I have the little "here be dragons" there in the corner, because it really exemplifies how little we know. Now let's jump ahead to the next era. Now this era is from the Planck time to about 10 to the minus 36 seconds. In this time, we still really don't know very much. We have some informed guesses. This is beyond known physics. The physics that we can actually measure today in our laboratory is much later in the history of the universe. It's still a fraction of a second, but it is much later than 10 to the minus 36 seconds. However, perhaps, you see all these perhapses here. Perhaps in this time, gravity and the subatomic forces have become different. It's kind of like one of them has frozen out and the rest are still liquid. Maybe, perhaps all of known subatomic forces are the same. Maybe not. This is all perhaps, and this guy looks rather confused, well, because he doesn't know the answer, and neither do I. Nobody really does. Although, these are reasonable guesses. They're informed, but you shouldn't believe that we know this. Moving ahead to the next era, this is called the inflation era. And this era is a theoretical conjecture. It's not proven. And so I have all sorts of caveats here. But what we think is that at about 10 to the minus 36 seconds, give or take, for every 10 to the minus 36 seconds, so you're from 10 to the minus 36, 2 times 10 to the minus 36, 3 times 10 to the minus 36, for each one of those little ticks of a very fast clock, the universe doubled in size. And it maybe doubled about 100 times. So 2 to the 100 is 10 to the 30. And that kind of expansion expands something from the size of the proton to bigger than the solar system. And it does it in, of order 10 to the minus 34 seconds. So in a tiny fraction of a second, something expands from basically zero size to the size of the solar system. Now, that does mean that if that's true, the universe expanded faster than light. And so that confuses people, and they say, well, that can't be, because everybody knows that Einstein says you can't go faster than light. And that's true. But what Einstein says is you can't go faster than light through space. It says nothing about how space itself can expand. So this doesn't break Einstein's laws. And so you ask, why do people think of this sort of seemingly ridiculous conjecture that the universe had this superluminal expansion period? And it's because there's real mystery. If you just take the ordinary traditional Big Bang that was sort of imagined back in the 1930s, it can't explain the fact that if you look to your left as far as our most powerful telescopes can see, and then you look to the right, again with the same telescope, what you see is that the universe to the left and the universe to the right are very, very similar. They look so similar, it seems that they must have been in contact with one another, because the standard 1930s Big Bang says that the two sides should look different, but they don't. And so this idea is a conjecture that says that at the very tiny early moment of the universe, things were touching, and then you had this super crazy expansion, and now the two sides, which seem like they have never been in touch with one another when we just look at it simply, well, maybe they did, and this is an explanation. So inflation is not proven. However, it's a well-regarded theory, and people are trying to prove it. And there are ideas, measurements looking into the sky, trying to get a handle on it. So it may be true. Now let's move forward to the next time, which is from 10 to the minus 32 seconds to 10 to the minus 13 seconds. Now this is the blurry time, and I have this picture, it's all blurry. Why is it blurry? Well, because now this is getting into a region where we still don't have data, but we're starting to get a real handle on things that we know. So it's speculative. There's an unknown number of forces and particles, but this is the region where we're really transitioning from the unknown to the known. So in this time frame, the universe has done that superluminal, that faster than light expansion, but now it's settled down and it's coasting. It is expanding and cooling, and we're going from very hot, high energy environment down, and eventually we'll end up into the universe we have now. But this is the realm where at the end of this period, we actually are starting to know stuff because we've taken measurements. And I'll talk about that in a minute. In this time period, this thing called the Higgs field. The Higgs field is the thing that gives the subatomic particles mass. When the Higgs field before, in the very early part of the universe, the Higgs field was zero. It didn't exist. And because it didn't exist, no particles had mass. When the Higgs field turns on, all of these particles that we're familiar with, the electron and some of the quarks, they now have mass. So this is something we're studying now. The Higgs field has been proven to be true. We've discovered it. So even though we don't yet know the exact temperature and moment at which it turned on, we at least are beginning to now make measurements about this. And when that happened, electric mass became a thing. I'm sorry, not electric mass, particle mass became a thing. Electric charge became a thing. Before that, electric charge didn't exist, mass didn't exist. And in this time, the particles that we're familiar with now, those quarks and leptons I talked about, they came into existence. And so I make the end of this era, this 10 to the minus 13 seconds, because the largest particle accelerator in the world is the highest energy one. It is built, it's in Europe, and it can actually collide together beams of protons, and the most violent possible collision that could be made in that accelerator can actually recreate the conditions of the universe as early as 10 to the minus 13 seconds. So after this time, we have data. Before that, we don't, but we know a lot about the physics at this early time, and we can project backwards a little bit and do that fairly sensibly. So let's just do a whirlwind of sort of the familiar territory. So I was talking about 10 to the minus 13 seconds. So that is a temperature of 10 to the 16 Kelvin, which is incredibly hot. That is the temperature, the highest temperature that the most powerful modern accelerator can create. And so that's why I say this is familiar territory. These are things that researchers at laboratories like Fermilab and CERN and and Stanford Accelerator in California, we can actually study the behavior of matter. So now we're getting a handle on, when I talked about that, the street light with the light under it, we're now getting into the place where the light is getting much brighter. If we move ahead, we can move ahead to a millionth of a second, just a simple millionth of a second after the Big Bang. The universe had cooled to 10 to the 13th, so that's 10 trillion Kelvin. It's still very hot. And at that temperature, the universe had cooled enough so that those quarks that I talked about, reminded you at the very beginning, had cooled enough to start coalescing into protons and neutrons. So this is the beginning of the time where ordinary atomic matter, like the kind that makes up you and I, came into existence. If we move ahead to about a second after the Big Bang, the universe had cooled to about 10 billion Kelvin. And this is interesting because before this time, these particles called neutrinos were bouncing around into all of the other particles because it was a hot gas, really a plasma. Things were interacting terribly, but at this temperature, the neutrinos stopped interacting. And this is very promising because those neutrinos then flew through the universe and they haven't interacted since the first second of the universe beginning. We have not yet detected these neutrinos, but people looking for a substance called dark matter, which I'm not going to talk about here, are making incredibly precise, sensitive detectors. And it is expected that in the next, perhaps decade or so, we will actually start seeing these neutrinos that were created just 1 second after the universe came into existence. And that will be, a really fun thing. If we move ahead to, say, a minute or 2 or 3 after the Big Bang, then the universe is cooled to 100 million Kelvin. And that's the temperature where protons and neutrons can then connect. And so helium, which is an atom which has protons and neutrons connected together, they started to form. Now, this is not the same as saying that the atoms formed, because the electrons, it's too hot. The electrons don't jump on the nuclei. So atoms are not a real thing that early, but the nuclei of atoms have now come into existence. By that time, there's no more, the nuclear physics stops, except for when, of course, stars start to burn. Then finally, we can move later to 380,000 years after the Big Bang, or after the, see, I say that, use the term wrong sometimes. After the moment at which the universe came into existence, the universe had cooled to 4,000 Kelvin. And this is the temperature at which hydrogen and helium atoms formed. Now, so at that time, the universe cooled to about this 4,000 Kelvin. Before this, it was so hot that electrons would be knocked off atoms. And so that had the feature that if light tried to penetrate the universe, it would bounce into electrons and it would get bounced around. The universe was essentially a glowing white fog before this time. But at this time, about 380,000 years, the universe cooled. And it cooled to the point where now light could travel through it. So it was still very hot, but light could travel through it. So this white, there's a reason why this is white. It's because that's the color of what the universe looked like at that temperature. But then the universe expanded and cooled and got yellow hot, orange hot, red hot. And finally, it faded into darkness. It faded to the point where the universe was completely black. And we call this, or astronomers call this, the dark age. So I'd like to have a brief interlude, because the universe did cool, and it cooled to the point where there was no light, but there was no light in the sense that our eyes couldn't see it. That doesn't mean that there was no energy out there. What happened is it had cooled first into the infrared and then into microwaves. So we can still see that fireball, that glow of the Big Bang is still out there. We can see it. And in fact, it was first seen in 1964, and it's called the cosmic microwave background radiation. So the temperature when the universe became transparent was 4,000 Kelvin. The temperature of the universe now is 2.7 Kelvin. It's minus 450 degrees below zero Fahrenheit, or minus about 270 degrees below zero centigrade. So we can see this now. This picture you're seeing is actually a photograph of the remnant fireball of the Big Bang. The universe, the temperature of the universe is quite uniform. It's basically 2.7 Kelvin everywhere, but there are tiny, tiny fluctuations in that temperature. Some are just a tiny bit hotter, and some are just a tiny bit colder. And you see that here. The red spots are a little bit hotter, and so that is a location in the early universe that was not quite as dense as the others. And the blue are where it's kind of cold, and so that's where it was more dense. And that becomes really important because those tiny little variations in density have a big effect on the future of the universe. So getting back to the dark age. So the dark age was from that about 400,000 years after the Big Bang. But after that, the universe cooled, everything was dark, but the universe was full of gas. And those gas was being pulled under the force of gravity in the clouds that over the course of about 1 million years became stars and galaxies. So here is a little video that shows that. So this is looking at the cosmic background, and we zoomed into a blue spot, a spot where it is more dense. And you see here this kind of weird stuff going on. And what's happening is that's gravity pulling hydrogen together into dense things, and that makes stars form. So you get these dense clouds, they get dense, and eventually they're dense enough that stars come into existence. And those stars then get pulled together into galaxies. And so that kind of is the transition from the early hot gas to the universe we see now. So you look on the left-hand side, that is the remnant fireball of the origin of the universe. You see that dark blue area, that's a cooler and denser spot. And as you move to the right, that's going forward in time. So you see very early in the universe, you had these clouds of gas with these bright stars. And as the time goes on, the gas starts going away because it gets pulled into stars. And you get on the right, that's the universe that we live in now. So by about 100 million years, the universe was becoming recognizable in the sense that the first stars had formed. So in the very early universe, stars didn't exist. And it took something like 100 million or 200 million years for the gas to first cool and then be pulled together by gravity into dense clouds that formed stars, and those stars gathered and made galaxies. In this picture here, this is an actual photograph by the James Webb Space Telescope that shows galaxies that existed in the first billion years or so of the history of the universe. The earliest galaxy that's been photographed, well, that's changed. It's changing rapidly. The last time I looked, it was about 200 million years after the Big Bang. And I seem to recall that there was some conjecture that maybe some astronomers had seen a galaxy that was formed even earlier. So not all of the galaxies you see here are among the first galaxies that were formed. In fact, some of them were 1 billion years or so after the Big Bang. But some of these galaxies you're seeing really are from the very time when the universe was a toddler. And so this means that, this is something we understand pretty well, because the fantastic thing about telescopes is the farther away you look, you're looking farther back in time. And that's because it takes time for light to get to us. And so if you look at something close, it wasn't that long ago. But if you look very far away, you can actually see what the universe looked like as it was coming into the existence that we see now. So that's absolutely fascinating. Now, so this kind of shows you the sort of astronomical history of the universe. So on the left, well, you see the point where the universe began. We see the inflation period. The universe got bigger. This is sort of a picture of the universe. On the left is earlier in time. On the right is later in time. We see that spotted pattern of the microwave background. That's when the universe became transparent. We then have the period of the dark ages. We have the period of the dark, the gas clumping together and making the bright stars. And then we go forward in time about 9 billion years. Now, the universe was created about 14 billion years ago. The expansion started. Gravity is an attractive force. So even though there was a very fast expansion in the beginning, gravity caused that expansion to slow down. And that was true for 9 billion years. But about 5 billion years ago, things changed. The expansion of the universe not only is still expanding, but it should be slowing down, and yet it's now speeding up. Something happened about 5 billion years ago that changed everything, because it seemed like the universe should slow down and slow down and slow down and not expand faster and faster. So I say it's the day the universe changed. It wasn't a day, of course, but about 5 billion years ago, the universe went from expanding and slowing to expanding and speeding up. And we think, and we have very good reason to believe, that the explanation for this is that there is a type of energy in the universe called dark energy. Dark energy is a repulsive form of gravity. And no, that doesn't mean it's disgusting. It means that it's pushing the universe apart. And so the universe is being pushed apart faster and faster. And of course, if we want to think about what's happening for the future of the universe, this has enormous implications for the future of the cosmos. And so we need to understand a little bit about dark energy if we want to predict the future. So this sort of summarizes everything I've said. We have the moment that the universe began at 0 seconds. At about 10 to the minus 36, we had that superluminal, faster than light expansion. Then we have at about 1 10 millionth of a second, or sorry, 10 billionth of a second, protons and neutrons formed. A couple of minutes, nuclei formed, so hydrogen and helium nuclei formed. Atoms formed at about 400,000 years after the Big Bang. Stars formed at about 100 million, and here we are now. So all of these things in the white, these are things that we have recreated in accelerators, and with some calculations, we actually understand all that white stuff pretty well. Now, the black stuff we don't understand as well. They're informed guesses, and maybe they're wrong, but they're not crazy. So now I'd like to just, I just took you, that was a whirlwind of information. So let's just take a breather and just recap what I've told you. We have a fair knowledge of what happened in the history of the universe from 1/10 of a trillionth of a second after it began to now, 14 billion years. All during that time, we know pretty much, we know a lot about that time. Now, when we go farther back, say from the 10 to the minus 32, that's the end of the inflation period, to the energy at which the LHC can actually study, these are informed guesses. Now, they're brave in the sense that we don't know this to be true. We don't know everything in there that we think is true. In fact, that's what my colleagues and I study. We're trying to get a handle on that better. But they're informed. I mean, we know something about what has to be, because if something really crazy happened at much earlier times, it would be difficult for it to evolve into the things that we've actually studied. So, this is brave, but it's not so brave. When we get back to the sort of inflation time, that's extremely brave, because we don't really know that inflation happened. We know that it's a great theory. It explains a lot of things. And that's why it's not so nuts, because it does explain a lot of things. It's a great idea that might even be true. So that's why it's extremely brave. But that's sort of the era of where we kind of have some reason to have some confidence that maybe we're not too off the wall. But then before that, it's pretty bonkers. We really don't know what happened before then. We can guess, but it's really guessing. So this gives you a sense. At the top in my nightlight example, is where we know, and then it gets dimmer and dimmer and dimmer to the bottom where it is actually pretty dark. So that kind of gives you a sense about what we know and what we think about how the universe evolved from the moment it began until today. But I promise to tell you about not only the life of the universe, but the birth and the death. So let's look into the future. And we'll stare in our crystal ball and try to make predictions about what the future should be. Now, there is a very wise philosopher from, I don't know, a couple of decades ago that had a very keen insight about looking to the future. And Yogi Berra, a baseball player from the New York Yankees, said, pretty tough to make predictions, especially about the future, but we're going to try to do that. And so we're going to try by saying, what happens? Because what dark energy, this thing that is causing the universe to expand faster and faster, is going to determine what the future of the universe is. But what if dark energy changes? What if dark energy reverses itself? What if instead of being a repulsive force, it becomes an attractive force? Well, if that's the case, then the future of the universe is that the universe expansion will reverse and it will contract back in a big crunch. Now, there's absolutely no reason to think that dark energy will reverse itself, but we don't understand dark energy completely, so it's at least a possibility. What about the opposite? What if dark energy increases? So we have a certain amount of dark energy in the universe today. What if it gets more? What if it increases and gets bigger and bigger? Well, we call this the big rip scenario, because that means that not only will the universe expand faster and faster, the expansion will get to be so fast that not only will it push distant galaxies away from us, it will eventually rip apart the Milky Way galaxy. It may rip apart the solar system. And if you have enough energy added, more dark energy, it could rip apart the Earth. It could rip apart the matter of the Earth, until a very distant future where you have individual atoms that have been torn apart and spread over the cosmos because dark energy has caused them to move away from each other so quickly. So that's another option, but only if dark energy increases, for which there's no evidence. So what if dark energy stays the same, which is what we sort of think will happen? Well, if that's what happens, then we have what we call the heat death. So I would like to describe what that means. And so let me first kind of give you some future highlights. Let's say that dark energy doesn't change. And then this is sort of a prediction of what the future will bring us. So about 5 billion years from now, the sun will heat up and get bigger. It will engulf the Earth and probably evaporate the Earth. And about 5 billion years from now, our nearest galaxy, we live in the Milky Way, there's another galaxy a couple of million light years away. It's barreling towards the Milky Way. In about 5 billion years, the Milky Way and Andromeda, the galaxy, will collide. I'm going to show you a movie about that, which is really cool. After about 1 billion years or so of this giant, the sun being a giant, the sun will burn out and it will become a white dwarf. So it'll be a little tiny burned out star that just is slowly cooling as time goes on. If we look further, 1,000 billion years, 1 trillion years into the future, the small stars will burn out. It turns out in astronomy, big stars die young, they live fast and die young. Small stars last longer. So smaller stars, stars smaller than the sun, they'll maybe last for 1 trillion years. In about 2 trillion years or so, this dark energy will have carried away all of the galaxies. There will be a point where all of the distant galaxies will have moved away and we won't see them. What we will only have is just the local galaxies, the Milky Way and Andromeda, will come together. And then when we look into deeper space, we'll see no other galaxies, just the one in which that makes up our Milky Way. Of course, the sun will be gone by then. If we look around at about 10 trillion years, the smallest possible stars, our sun is a certain size. There are much smaller stars. There's stars half the size of the sun, 10% of the sun. When you get down a little bit less than 10% of the sun, at about 8%, below that, they're not stars. It's just not big enough to burn. So if you look at the smallest possible stars, they will burn out in about 10 trillion years, so long after our star is come and gone, but even they will burn out. So I see here that protons decay. Now, we don't know if protons decay, but they might. And what we know is we know if they decay, they live a long time. They live at least 10 to the 35 years. So that's a 1 with 35 zeros. That's incredibly far in the future. Maybe they don't decay. Maybe they do. But if they do, it'll be after that. Once all the stars are burned out, the only thing that's left around are black holes, which are stars that were so big, they exploded, and they crunched all the core of the star down to the point where no light can escape. But black holes do evaporate. Stephen Hawking determined a thing called Hawking radiation, which says that these black holes do slowly evaporate over time. And black holes, the mass of the sun, will evaporate in about 10 to the 66 years. At the center of galaxies, they're much bigger black holes. But even by 10 to 100 years, the supermassive black holes will evaporate. So by that time, the stars will burn out. Maybe protons will decay. If they do, the black holes will evaporate. And what happens is you fade to black. That's it. That's over. So I want to show you here a little bit of movie. We see a timer going down here. This is moving, 500 million years, 0.6 billion years into the future. This is supposed to be the Milky Way galaxy. It's a barred galaxy rotating out in space. And into the picture, we have the Andromeda galaxy and a smaller galaxy called Triangulum, which we won't worry about too much. And this little movie is going to show what will happen over the eons. We see that Andromeda is barreling towards the Milky Way. And at a time of about, something like 4-ish billion years, the two galaxies will collide. And this is the sort of mess that you will see. You'll see the two galaxies will blow through one another. They will shoot stars out into space. Individual stars will be safe because it's very rare that stars themselves would interact. But what will happen is the galaxies will pass through one another, back and forth, and they will finally settle down into a single galaxy that you see here. Now, remember, the two galaxies were originally spiral galaxies. What you're seeing now here is an elliptical galaxy. So it doesn't have those beautiful spiral arms. You see there are stars floating around the outside. They will slowly accrete and come back to the center. And you'll also notice that the color has changed. The galaxies were originally blue, but over time, the stars are aging and dying. And ones that were vibrant, young, bright stars are now they're dimmer. They're more yellow. They're getting closer to red. So this is what happens about 8 billion years from now. What happens as time goes on? Well, what happens as time goes on, we're seeing that those stars, didn't do that. There we go. We're seeing those stars are starting to fade. They're cooling. They're turning redder and redder, and they're getting dimmer, and they're fading away until in the very distant future, when all of the galaxies are far away from here, and all that's left is our Milky Way and Andromeda galaxy together, the stars are burned out, and we fade into black. This is what science thinks the future of the universe will be. A long, dark night where everything cools and there's nothing. Now, that is a bit of a depressing thing, and you can be forgiven if that sounds like something that we just don't want to think about. So let's forget about this. Let's look into the past. Let's try our very best to try and look to what happened before the universe began. Now, remember, I told you before about 10 to the minus 44 seconds, our theories break. And so we're sort of looking through this mystical shroud, this shroud and covered door, and trying to look through it to get a handle of the universe, how the universe came to be and what happened. So let's just talk. We're going to talk about the beginning. things you might have heard. So there's some real misconceptions about the moment the universe came into being. So you might have heard that before the Big Bang, there was no space and no time. Now that is not an unreasonable thing. But what it is it is a statement from general relativity. General relativity remembers Einstein's theory of gravity. And in his theory, it says that as you get to zero time, as you get to the moment the universe created, space didn't exist. Time literally didn't exist. There was no space. There was no time. It was in the creation of the universe that space and time came into existence. But we know, I've told you that general relativity breaks down this early. And the moral of this is when someone talks about these extreme events, you have to keep in mind the differences between a specific theory and a broader idea. I mean, the theory of relativity, which is a very good theory, there's a lot of reasons to believe it. It says that space and time didn't exist, and that's fine. But if the theory doesn't work, we should be cautious. So let me tell you what the Big Bang isn't. And this little movie I'm going to show you. This shows you what people think the Big Bang is, but it's not. And what they think is this: that all of the matter was in a singularity, and all of a sudden that singularity exploded. It threw the mass and matter across the universe, cooling, expanding, forming stars and galaxies, and coming to where we are now. So that is very common. This is what people think the Big Bang was, but it really is. This is what I like to call the firecracker explanation of the beginning of the universe, where it says that all of the matter of the universe was in one place, which then exploded. And if that was true, then it's easy to think that there must be, an outer edge of the explosion. There's a place where there's matter, and there's a place where there is no matter, because that's outside of the blast, so to speak. But that's not what the Big Bang says. It's not what the theory of the Big Bang says. The Big Bang, it's very, very tricky and complicated. So to understand this, we have to know the difference between the entire universe and the visible universe. The visible universe is what we can see using our powerful telescopes and looking out into the cosmos. And in the current day, the visible universe, the farthest we could possibly see, is about 92 billion light years across. However, we know from measurements, which I don't have time to talk about, we know that the universe is bigger than the universe we can see. We know that the universe is at least 125 million times bigger, volume-wise, than the visible universe. So this picture kind of shows us what the situation. You have the visible universe, which is the yellow, and you have the gray, which is the total universe, which we don't know how big it is. It could be infinite, or it could be just big. We don't know the size. Now, the reason I drew this is because this is kind of like what the situation was near the moment where the universe began. Now, the entire visible universe was compressed to a smaller size than you see here, but it wouldn't, if I made it as small as it was, it wouldn't be visible. So give me some artistic license here. But what the theory using relativity says, it says that the beginning of the universe looked like this, where you had all of the visible universe compressed to a small point, and then something happened and it caused it to expand. So here you have the visible universe expanding. That's our universe. The gray stuff is still the universe that we can't get to, but this is what this is what the theory of the Big Bang says. It says that space expanded. It's not the firecracker universe. So let's talk about some crazy ideas about how the universe could have come to be. So this is an idea, crazy idea number one. This says that universes butt off from other universes. So we have a picture here of an existing universe, and I have this little weird blinking thing, and that's only because I couldn't think of a better way to do that with PowerPoint. I was looking for something more shimmering. But the idea here is that in ordinary space, in the same way that inflation occurred, maybe in that little spot inflation starts over again. And if that's true, that little spot in a existing universe will then expand, and that's a new universe. And so you have essentially universes, spots in existing universes becoming new universes. And this sort of shows the idea, the bubble universe. On the bottom, you have a single universe, and then you have 3 universes expanding off from that. And those universes can then expand other universes. And that's kind of the idea, is that universes come from other universes. Now, these universes can't talk to each other, and these different colors are meant to indicate different laws of nature. So in some universes, the laws of nature are such that life can form, and some there aren't. But that's what this idea is, that the universe didn't really have a beginning. Each one of these universes had a beginning, but they all came from a prior universe. This is an idea. It's kind of a crazy idea. You shouldn't believe it necessarily, but you should know that it's a possibility. Another idea, and this is also very, very crazy, is that universes, there's this misleading word. Universe means everything, but maybe there are multiple universes. So in some higher dimensional space, there are extra universes. So in the same way that, 2 balls can move around in 3-dimensional space without touching one another, maybe the universes are moving around in some higher dimensional space. So this kind of funky, groovy color thing is some higher level space. And here you have 2 universes. And what happens if those universes float around in this multi-dimensional space? Well, they could collide to one another. And the idea is that if that happens in the collision, that collision will heat the universes up, and that will erase everything that happened before, and that will start basically a new universe. So that's another really kind of crazy idea about how our universe maybe came into existence. Maybe it's just a previous universe that crashed into another one and has been heated up. So I've given you a couple of ideas about what happened before the universe, our universe, began. But remember, we don't know really what happened. We don't know, if anything, certainly before the Planck time, and we're pretty fuzzy even after that Planck time. So there's a lot we don't know. These are just speculative ideas. And so, you could ask, what's the real answer? What really happened before the universe began? And, all I can tell you is, I don't know. Nobody knows. Anybody who tells you they know, really, they don't know. They were just thinking about crazy, cool ideas. So before we close, I'd like to point about some reading. These are reading for people that want to look into this more deeply. There's a recent book written by Katie Mack, who's an excellent writer, called The End of Everything, and that talks about the end of the universe. And then there are 2 books, one by Brian Clegg called Before the Big Bang, and another one by Laura Mersini Houghton, which just came out. And if you want to read more about this, because I could only scratch the surface of this in an hour-long talk. And then in the bottom, this isn't for you, the viewers tonight, but this video will be made into a YouTube video. It'll be put on the channel. And I'm going to put in the description links to other videos. So everything I talked about, I went through really quickly, but I've made other videos, and they cover some of these topics in more detail. And so if you decide to rewatch this and then look at the other videos, it'll give you a much bigger and better idea of what's going on. And maybe you'll learn another thing or two that I just didn't have time to go into now. And so I'd like to thank everyone for listening.